In this video, we'll continue our discussion of exploratory factor analysis in this lecture set by focusing on some details about the extraction methods that are available to us and how we can determine the number of factors that we should be pulling for our factor analysis. So for the factor extraction method, this is one of the first decisions that we need to make and is very strongly tied to some of the mathematical calculations. Again, it's worth mentioning, I'm going to skip the math and the details, and because of that, I'm not actually going to discuss in depth these particular extraction methods. I will mention some of the pros and cons of each of these and where they tend to be commonly used, but I don't want you to feel if you're walking away from this and like, hey, I don't understand the details. Yeah, I get that, and that is part of the limitation of this. So if you want to understand more of the details, I advise you to check out a statistics textbook on the details of factor extraction methods, etc. That'll be a lot of matrices and a lot of matrix decomposition and some details regarding how we optimize the matrix decomposition and what function we are optimizing within that. That's the real distinction between these methods at a very meaningful mathematical level. Again, we're going to skip over all that and just focus on the big picture. And in this lecture set, I'm just going to talk about three options that I think are very common options that you may select. The first one is principal components analysis, or PCA. Then we'll talk about factor analysis, sometimes called like principal axis factoring, or just factor analysis. And I know it's pretty confusing that exploratory factor analysis has a factor extraction method called factor analysis, but c'est la vie. And then we'll talk about maximum likelihood as a potential option for this. And depending on what other lectures of mine you've seen, you'll notice that a theme's coming up. Maximum likelihood appears over and over again, and maximum likelihood, again, is a broad statistical approach and is very applicable here as well, where we maximize a likelihood function. Regarding exploratory factor analysis, each of these have specific places where they're pretty useful and have specific places where they're not very useful. And so we'll discuss those in just a second. The ideal case, though, is that all of these give the same result. And typically, they do give very similar results. So if you ran, say, exploratory factor analysis using principal components analysis as your extraction method, and then reran it using maximum likelihood, ideally you're going to get the exact same interpretations as one another. And this is actually good evidence for you that the factor loadings are not dependent on your extraction method assumptions, that your factor loadings are actually just coming from the data. So, and I would argue that this is very typical, that these really do give the same solution, or qualitatively the same solution. That is, the interpretations would be the same either way, no matter which of these options you use. There are a couple of cases that that's not true. Again, it's in those cases where that's not true, that is when the results differ between these, it can be important to know which to trust and which one is most relevant or makes the best assumptions, decisions, etc., regarding the way in which you're trying to use that particular analysis. Of course, if they disagree, it may be worth reporting both sets of solutions to your readers, either in an article or in a presentation, and just mentioning, like, these are the differences. This is the differences in assumptions we're making with our kind of first mathematical step, this extraction method. And based on these assumptions, I'm getting different solutions. Here's one solution based on this set of assumptions. Here's a second solution based on this set of assumptions. And the difference in solution isn't related to the data. The difference in solution is related to the assumptions we're making with our extraction method. And that itself can be important information to know. All right, so let's talk more in depth about each of these options. And for each one, I want to kind of go through and list maybe pros and cons. And again, in the best case scenario, all of these agree. So take the pros and cons in context that these are going to tend to agree with one another. Not that these are massively different, and they're different, but they're going to tend to provide similar solutions to one another. So take everything within that context, please. All right, so for principal components analysis, this is really useful when creating like a factor combination score. So in a previous video in the lecture set, we discussed how the multiple regression, if we wanted to like combine variables that are highly correlated, we could run a factor analysis to create a combination score. This is where principal components analysis is very often classically used. And it makes a lot of sense to do so because you're maximizing the amount of variance explained within principal components. So this is a pretty useful method for applications like that, where we're really going for those factor combination scores. It's a very numerical approach. I don't particularly care about the interpretation. My goal is just to get the numbers. On the flip side, this isn't particularly good when trying to understand or study the underlying structure of this, and it's because the variance that it's maximizing is the variance that's there in addition to variance that couldn't possibly be maximized or observed because it's not included in the correlation with all the other variables. So within this, again, take principal components with a grain of salt when using it for interpretation, and we do have potentially some better options. The factor analysis approach, I think, is better when it's trying to understand the underlying constructs, and this is my default one. If I'm making, again, the factor combination score, I might use a PCA, but and PCAs are faster. I guess it's worth mentioning. I don't think I have it on the slide, but that's why they've been used historically, is because they are faster. But the factor analysis tends to be more handy when I'm trying to actually understand the constructs or the factors that I'm creating. I think the loadings tend to be a little bit more representative of what I should expect in terms of loadings of items or variables on their factors. And the other thing that's interesting about this, and this will become more important in a second, is that with factor analysis, this tends to be a little bit more useful when my distributions of variables are unknown. Now, because it only uses the common variance, it doesn't explain variance as well as, say, PCA. And because of that, when I'm just seeking to create those combination scores, again, maybe PCA is a better option. Right, so the last one here, maximum likelihood, very strong performance when data are normally distributed, but actually that's the pro and the con, is factor analysis doesn't necessarily tie as closely to those data distribution assumptions as maximum likelihood does. And so when the data aren't normally distributed, factor analysis tends to be better. Now, I say aren't normally distributed. The data do not have to follow a perfect normal distribution for maximum likelihood to be a reasonable option. What I mean is that if they are extraordinarily not normally distributed, maximum likelihood is going to break potentially pretty badly, whereas factor analysis might perform better. So don't feel like that because it's not perfectly normal and because your projected normal distribution on your histogram is slightly off on one particular peak point that I broke maximum likelihood or something like that. This is really talking about more moderate to severe violations of normality in this particular case. So again, 3 options: principal components, factor analysis, and maximum likelihood. My personal default is factor analysis. So I tend to use factor analysis when I'm analyzing survey-style data. For me, again, I'm trying to understand the underlying constructs. So principal components analysis isn't what I'm particularly interested in. I use factor analysis. I also just don't want to assume normality of my items when I'm analyzing survey data. And again, different people may have different opinions on that, and different surveys even may have different reasonablenesses of assuming normality. But in the data I tend to work with, I just don't like making that assumption. I don't like having to check that assumption, so I stick with my factor analysis. I still probably should make sure it's not too crazily non-normal. But factor analysis, again, alleviates that explicit and a more vulnerable assumption that exists in maximum likelihood. All right, so let's throw that away for a second and focus on the number of factors. That is, how do we figure out how many factors we should extract from our number of variables? And this question is, again, very similar to selecting the number of clusters in cluster analysis. You're seeing some alignment here. Again, in clusters, we were looking for the number of clusters with participants. In factors, we'll be looking for the number of factors with a certain number of variables. And also similar to cluster analysis, there's a bunch of options that we can select between when determining how many factors we extract. We'll, in this lecture set, discuss 3 of the options. One is by examining the eigenvalues of the different factors that we could extract. Another is by looking at the scree plot, which is actually similar, but in the scree plot, we look at something different in eigenvalues. We just have an eigenvalue cut. And we can also look at something called parallel analysis that we will discuss further. Now, it's important, again, to make the correct decision. And with the previous one, they tended to agree. With these, it's fantastic if they agree, but frankly, typically eigenvalues, scree plots, and even sometimes parallel analysis all tend to give you a different number of factors. Now, when that happens, what we do, or what we can do, is to run all of the factor suggestions from each of the recommendations and see which one is most interpretable. But it is important to realize that misspecification of the number of factors can drastically impact your interpretations. And so we really want to not misspecify the number of factors if at all possible. That's our goal. All right, so let's jump into each of these, starting with eigenvalues. So eigenvalues, what are they? Like that, I don't know, maybe that doesn't sound familiar. It reminds me of a college math class I took years and years ago. But ultimately, eigenvalues are a set of numbers that represent association or importance. So in this particular case, think eigenvalues with a higher value are indicating that factors are more important. Ultimately, when we standardize our variables to go into a factor analysis, which SPSS does by default, an eigenvalue of 1 represents the variance contribution of a single factor. So in that particular case, if I have a single variable. So if I have a factor with an eigenvalue of 8, that would be, quote unquote, explaining the variance of 3 or of 8 different items. So if I have a factor with an eigenvalue of 8, that would be explaining the variance of 8 items. Yes. Sorry, I'm getting a bit tongue-tied here. So again, higher eigenvalues represent more contribution. Well, if an eigenvalue of 1 represents the variability contributed by a single variable, it kind of makes sense that we would want to keep factors with an eigenvalue of 1 or better. That is, I only want to keep factors if they're contributing as much as an original item did. I don't want to keep factors that aren't really contributing. I want to make sure my factor is contributing some, and that's how I can determine how many factors to keep. And again, a kind of a intellectually reasonable cutoff would be, okay, well, I can just keep factors that contribute more than one eigenvalue of information. And this idea actually has a name. It's called the Kaiser criterion, and it is a very classic way of determining the number of factors to keep. Now, a bit of a spoiler ahead, this actually tends to be a bit antiquated because it tends to give too many factors, and we can run simulation studies to kind of test this out with random data and see, actually, yeah, maybe this doesn't perform as well as we think. But again, it's very classic. It's a very easy way to determine. It's very easy to automate. And so you will absolutely, if you start reading any literature that uses factor analyses, see this eigenvalue of 1 cutoff used even to this day very often. Sometimes they'll call it the Kaiser criterion. Sometimes they'll just say we kept the number of factors as long as the number of factors was had eigenvalues greater than 1. And again, it does make logical sense when you interpret what an eigenvalue means, but in practice, it tends to not be as effective as our other two methods. So the second method is a scree plot. And again, this is very similar to something that we talk about in cluster analysis, where in cluster analysis, we also look at a scree plot. In our scree plot, the y-axis are the eigenvalues, where the x-axis is the number of factors. But this is an important distinction. Unlike in cluster analysis, we select, when we're interpreting the scree plot, the number of factors before the elbow. So in cluster analysis, when we looked at a scree plot and we found an elbow, we selected the number of the number of clusters at that elbow. But in factor analysis, when we find an elbow, we'll select the number of factors before that elbow, and we'll look at an example right here. So we have our scree plot, and I see there's a potential elbow at maybe 2 factors, and then there looks like a definite elbow at 1, 2, 3, 4 factors. Looks like a pretty sharp elbow to me. And so in the exploratory factor analysis, we select the number of factors before the elbow. So if I'm circling 4 factors, that 4th dot on this plot from the left as my elbow, I'd put a little circle around that and say that's the elbow. So in my factor analysis, I would select 3 factors to be included. Again, the number of factors before the elbow occurs. Ultimately, this is not just to be difficult. The reason we do that is because the y-axis on a exploratory factor analysis scree plot is a different quantity than the y-axis on a cluster analysis scree plot. On a cluster analysis scree plot, the y-axis represented error, that is, how much error was in the data. And on the exploratory factor analysis scree plot, the y-axis represents eigenvalues, or the number of the amount of variance explained by each number of factors. So in this particular case, again, they represent very different things. And because of that, we want to be careful and just be very explicit that if you've performed a scree plot analysis for a cluster analysis, you're not looking at it the same way as exploratory factor analysis, where we have to look at scree plots very differently. All right. So parallel analysis really involves looking at a scree plot, but adds a line for random data. And this is the graphical way. We'll talk about a tabular way to do it in a second, but this is the classic way to do a parallel analysis. So think about a parallel analysis as we took literally random data with as many variables as we have in our observed data. So I took all those variables and I just made random data, just threw random data in each variable. And then I ran a factor analysis. The idea is, in my observed data, I want to select factors that contribute more than they would have if they just had random data. So I want to select factors that are actually making a contribution to my interpretation. The goal is to keep factors, again, where the eigenvalue is above that of random data. And it's important to recognize that if I reran this graph over and over and over again, it's going to change slightly because I am actually generating random data on my computer to create the graph. And though that change may feel like, hey, it's changed every time, so it's arbitrary, actually it tends to stay pretty close. It tends to give pretty consistent interpretations. If you know a little bit about computers, you can set a seed to make sure that the random number generators on multiple runs are consistent. But still, even if it changes slightly from run to run, it tends to be more objective than a scree plot in terms of where we should select. And ideally, hopefully, this agrees with our scree plot. So here is a scree plot in the blue, and you'll see the parallel analysis superimposed in a red dotted line. And you see that at 1, 2, 3, 4, the fourth X, which stands for the fourth factor, that the fourth factor does just about random. So it doesn't seem to be doing any better than random data would at a fourth factor. On the other hand, the first three factors do seem to be doing better than random data. So we would keep factor 1, factor 2, and factor 3 because they seem to be contributing more than they would if this were just random data. And that's how we interpret a parallel analysis. This is a very, very strong method. It's a very convenient method, and it's a very modern method, way to look at the number of factors to extract in a factor solution. I really like it because I really like the interpretation. That is, I really like that we're trying to pull factors that contribute better than just randomness, and that just makes a lot of intuitive sense to me and seems to be pretty easy to explain. So I really quite like this parallel analysis approach. Unfortunately, we can't do a parallel analysis in SPSS. And so that's a bit of a pain. On the other hand, we can get a table of eigenvalues from SPSS. And based on this, we can compare this table of eigenvalues to random data generated in an online calculator. So this is okay because, frankly, the random data generated, it doesn't have to be generated on my computer. It's just random data. Now, I do have to tell the computer how many total observations I had and how many total variables I have, so it knows how much random data to generate. But it's just generating literal random numbers, so it doesn't matter if my computer does it or a computer halfway around the world does it. It just has to generate the random numbers and run this factor analysis on the random numbers. So as long as I can do that, I can pull the random numbers from an online calculator and then run a parallel analysis in a table form. Now, what I'm going to be looking at is I used an online calculator to pull this. I really just Googled parallel analysis, and one of the top clicks was, hey, here's an online calculator to give you the random data, and then you can compare that to your data. And it was a very, very quick process to find. Now, in interpreting this, the left is my data, and the right table is the data that I found on this random online calculator. I'm going to be comparing my total eigenvalues for each factor number with the percentile eigenvalues for the random data. And it's worth noting the random data doesn't just calculate the average, it calculates maybe the 95th percentile. So it's trying to give you a 5% error rate as opposed to something a little bit more. And that's a typical error rate that we use in statistics. So that does seem to make sense. And so I'm going to be comparing, and any time, just like the scree plot, if my data's contribution is larger than the random, then I keep that factor. But as soon as my data's contribution becomes equal to or smaller than random, then I drop that factor. So in this particular case, looking at these two highlighted columns, I'm going to highlight the rows that I'm looking at. In the green row that is 3 factors, I see that the total in my data, that third factor is contributing 0.851 eigenvalues, or 11% of the variance. And if I look over, I see that the percentile eigenvalue is 0.58. So because my data has a higher eigenvalue than the random data, I'm going to keep the third factor. But if I look at the fourth factor, I see that the eigenvalue in my data set is 0.374 eigenvalue, and the percentile eigenvalue for the random data is 0.522. So my fourth factor is contributing less than would be expected by random data, and so I'm not going to keep a fourth factor. In this particular case, because the third factor is the last factor with an eigenvalue in my observed data larger than the eigenvalue found in random data, I'm going to keep 3 factors in my factor analysis. We just talked about 3 possible options. Which one should you use? Well, that's a good question. In the best case scenario, all of them agree, so you don't really have to determine one way versus the other. But again, in practice, you really have some decisions to make. The best, in quotes, is probably parallel analysis because it actually compares to actual random data. And so I can have a feel for which of my factors are contributing better than random which tends to be what I'm trying to determine when determining how many factors to keep. So parallel analysis is a good default, but parallel analysis isn't always available. That is, not all softwares do parallel analysis, as we just talked about with SPSS. So the scree plot is actually also a very good default. It's easy, it's implemented in virtually every software that you'll have, and it actually does a really good job. So if parallel analysis and scree plot suggested two different things, I would probably run them both and go with the one that made the most sense in terms of interpretability of the factor analysis solution. But if I'm just doing a default parallel analysis scree plot, again, I would probably do both of those. And again, if you're doing the graphic parallel analysis and scree plot, in the parallel analysis graphic, you will see the scree plot. So you can see elbows on the scree plot and kind of do them both at the same time. You don't have to pick. But yeah, I'd probably stick with parallel analysis, maybe scree plot. The Kaiser criterion I mentioned because it is classical. You will see it used in some publications still. It's arguably the easiest because, hey, anything above an eigenvalue of 1, keep. Anything below, don't keep. But it is very fallen out of favor, I would say. Some journals do it. I would consider that to be not statistical best practice. And because scree plots are so easy, even if they are a bit subjective, I would highly recommend utilizing scree plot. And if you wanted something to be a little bit more objective, maybe a little bit more fancy, maybe a little bit more reliable, you could implement a parallel analysis. Ultimately, though, any of these could have an argument for them. Again, scree plot's easy and it's available, and it tends to be very reliable and very good. Don't take my comments on parallel analysis being the best to indicate that scree plot's not good. If scree plot earned a 90% on the test, maybe parallel analysis earned a 98% on the test. Both of them got an A, so they're both very good methods, I think, that can be used. Kaiser criterion, unless the journal forced you to use it, I would not use it. And even if a journal forced me to use Kaiser criterion, I would double check using the others to try to make sure that I'm not completely misspecifying the number of factors. Again, that misspecification can have drastic interpretations in terms of, or drastic implications in terms of interpreting the model. But when in doubt, try them all. That is, run the parallel analysis, run the scree plot and interpret it, run the Kaiser criterion with, keep the number of factors where the eigenvalues are greater than 1. And run each of those factor analyses and find solutions for each of them and try interpreting them and pick the one that gives the cleanest and most interpretable solution. And I think that's a very reasonable goal. The end goal of factor analysis is to come up with interpretable solutions. It's by definition and by design an exploratory style analysis. So I think looking at all of these options and selecting the option that makes the most sense in terms of interpretation is an easy choice when you may be in doubt as to which one to select. And again, you're exploring your data. This is exploratory factor analysis. It's in the name that this is exploratory. So don't feel like you're cheating. Just describe what you did. I did all of them. I ran all of them, and I picked the best solution, the one that made the most sense for me. And that would be what you write in your paper. And I think authors and editors can nod along to that and say, okay, well, that makes sense, and it's good you checked the different options for these. All right, so we just discussed extraction method and figuring out the number of factors. In the next video in this lecture set, we'll talk about the different factor loadings and factor rotation options before we jump into a software example.